Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at injective, surjective, and bijective functions. So let's start off with the meaning of surjective. A function is said to be surjective or onto if every element in the codomain is mapped to by at least one element of the domain. It basically means the codomain is the same as the range. So those words might not mean anything to you now. Hopefully they will after we do some examples, and when you go back and read the definition, it makes more sense. So this function here is surjective or onto. Those words are used interchangeably. It doesn't really matter which you call it. So the reason that this function is surjective is because each element in this codomain is mapped to by at least one element over here. Basically, none of the elements here in the codomain are lonely. On the other hand, if I look at this function here, it's clearly a function, but it is not onto. It is not surjective. The reason is we have an element that's lonely. E is not mapped to by any element from the domain. You only need one such element to conclude the function is not onto. What about from graphs? Well, here we have two graphs that are mapping the real numbers to the real numbers. So this function here is not onto, it's not surjective. So why is that? Well, when we're looking at functions, we're mapping x values to y values. You can clearly see here that there are some y values, namely negative ones, that are not mapped to by any x value. On the other hand, if we look here, remember the arrows mean that it goes forever in that direction. If it goes forever, eventually each value of y will be mapped to by some x. So this is onto. There are no values of y that are not in range. All right, let's now take a look at what it means to be injective. So a function is injective or one-to-one if every element in the domain is mapped to one and only one element in the codomain. Again, I'm hoping that definition will become a lot more useful to you after we do some examples. So let's look at this function here that's clearly a function. It turns out that this one is injective or one-to-one. So why is that the case? Because there are no elements here that are mapped to by more than one element in the domain. In other words, each element in the domain goes to a different element in the codomain. It doesn't matter that 6 is lonely. It means that this function is not onto, but it is certainly one-to-one. On the other hand, if we look at this function here, this is clearly not one-to-one. It is not injective. The reason is we have a case where different elements in the domain map to the same element in the codomain. So this one here, if you like, is greedy. So we want none to be lonely in order that it's surjective, and we want none to be greedy, in which case it's one-to-one. So once again, it only takes one counterexample. It only takes one case where something goes wrong for the function to not be one-to-one. Now, if we have the graphs of a function, it's really easy to see whether or not it's injective. We use the horizontal line test. You've seen before the vertical line test. The horizontal line test works in a similar way. Is it possible to draw a horizontal line that hits the graph more than once? You'll see here that I cannot draw a horizontal line that hits this blue graph more than once. If you can't draw such a line, then the function is one-to-one. It passes the horizontal line test. On the other hand, if I look at this function here, it's very clearly possible that I can draw horizontal lines that hit the graph more than once. This first line hit the graph, in fact, 3 times. So it's not one-to-one. That's what the horizontal line checks. It checks, is there a y value that is mapped to by more than one x value? All right, let's now take a look at what it means to be bijective. So basically, a function is said to be bijective if it's injective, one-to-one, and also surjective, onto. So when a function is bijective, it makes things nice and easy. There's basically a perfect correspondence between elements of the domain and elements of the codomain. So it turns out, as we'll see in subsequent lessons, a function has an inverse when and only when it is bijective. That's why it's important. So let's look at these three examples and determine whether or not the function displayed is bijective. So if we look here, this function is not one-to-one because these two elements, different elements of the domain, map to the same element in the codomain. This is not one-to-one because there's a greedy element. It's also not onto because there's a lonely element. There's an element here in the codomain that's not mapped to. Because this is neither injective nor surjective, this is clearly not bijective. On the other hand, let's look here. So this function here is clearly onto. There are no lonely elements. However, it is not one-to-one because there is a greedy element. So it needs to be both injective and surjective. It needs to be both one-to-one and onto to be bijective. This is not bijective. On the other hand, this function here is bijective. If you want to check whether or not a function is bijective, check whether it's one-to-one, then check whether it's onto. Now this is clearly one-to-one. There are no greedy elements. There are no elements here mapped to by more than one element of the domain. So this is clearly one-to-one. It's also onto because there are no lonely elements. There are no elements here that are not mapped to. So because this is both one-to-one and onto, it's both injective and surjective, it is bijective. It means that it will have an inverse. So you can see with bijective functions, there's like this perfect one-to-one pairing between elements of the domain and elements of the codomain. All right, let's now look at determining whether a function is bijective merely from its rule. So we're going to consider the function fx equals x cubed as a function from the real numbers to the real numbers and determine whether or not it's bijective. In order to do that, we need to determine whether it's injective, one-to-one, and surjective, onto. So let's start with injective. Is this function one-to-one? So that means if I know the element in the range, is it mapped to by only one element from the domain? So if you have something like 8 in the range equals x cubed, you can solve this just by cube rooting. You get x equals 2. If I have negative 27 in the range equals x cubed, then x equals minus 3. It turns out you always get this happening for this function. If you know the element in the range, then you can find the element in the domain by cube rooting. So this function is in fact injective. Is it surjective, however? Is it true that any number could be an output? Again, it is true, because you can take a negative number, positive number, you can take any number you want and cube root it. You can cube root any number at all, and that means that any real number is in the range here. So it turns out this function is injective and it is also surjective, so that means yes, it is bijective. So what about if I restrict the function here to z3? So remember, z3 is the set of all integers modulo 3. It only includes the numbers 0, 1, and 2. So because there's such a small number of elements, we can draw up a map here, 0, 1, and 2. So what we're going to do is take these values in the domain, these ones here are our x values, and cube them. So in mod 3, 0 cubed is still 0, 1 cubed is still 1. Now 2 cubed is 8, which is equivalent to 2 mod 3. So it turns out each element is just mapped to itself. So we can see that this clearly is one-to-one, it's injective, because there are no greedy elements here. It is surjective because there are no lonely elements here. So once again, this function is bijective because it is both 1-to-1 and onto. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.